All right, let's dive into a really powerful idea from math that helps us make sense of a world where 1 plus 1, well, it doesn't always equal 2. It's called generalized measure theory, and I promise it's way more intuitive than it sounds. Just think about this for a second. Imagine you've got a TV with a perfect crystal clear picture, but the sound is just awful. Or maybe the sound is incredible, but the picture is a blurring mess. On their own, neither one is a great experience. But when you get both, a high-quality picture and high-quality sound, that whole experience is just so much more than adding good picture and good sound together, right? That magic extra bit is synergy. But how do you actually measure that?
And that little thought experiment with the TV, it actually points to a really big fundamental challenge. It shows that the way we intuitively value things often completely breaks the simple rules of addition.
And look, this isn't just about TVs. When we try to evaluate anything complex, the different pieces interact with each other. Sometimes they click and create synergy, making the whole thing way better than you'd expect. Other times you get redundancy where things kind of overlap and you get less bang for your buck. And a lot of the time, you're just dealing with plain old uncertainty. Simple addition it can't keep up with any of that.
So, to really get a grip on the new solution, we first have to look at the old way of doing things. For centuries, mathematics had a very strict system for measuring stuff, and it was all built on something called classical measure theory.
So what's a classical measure? Really, it's just a fancy term for a rule that assigns a number, a value, to a set of things. This is the bedrock for concepts we use every single day, like figuring out the length of a rope, the area of a floor, or even the probability of something happening.
And the absolute, non-negotiable heart of this whole system was one single, really rigid rule: additivity. It says that if you take two separate, non-overlapping things, the measure of them combined has to be the exact sum of their individual measures. No ifs, ands, or buts.
And to be fair, this rule works beautifully for a ton of stuff. If you lay two pieces of wood end to end, of course their total length is just the sum of the parts. Same goes for area, for weight, and for old-school probability. It's totally intuitive and reliable in those cases.
But over time, people started to feel like this rule was a bit of a straitjacket. I mean, what about when you've got measurement errors? Or when you're trying to put a number on something subjective, like an expert's opinion? The real world is just messy. And a lot of mathematicians started to argue that this strict additivity rule wasn't flexible enough to describe it.
So all this frustration, it actually led to a huge breakthrough. And get this, instead of adding more rules to try and fix things, the solution was to throw almost all of them out. The result was a measure that was radically simpler and way more powerful.
I mean, just look at this. This slide says it all. On the left, you've got classical measures with this whole laundry list of requirements you have to follow. But on the right, generalized measures have just one core rule. The measure of nothing is 0. That's it. That's the whole foundation. Everything else, including that strict additivity rule, is now totally optional.
Now, you might be thinking, doesn't that just lead to chaos? If you throw out the main rule, doesn't everything fall apart? But it's actually the complete opposite. This one simple change unlocks this amazing new toolbox that's so much better for describing the complex, interconnected world we actually live in.
So, what's in this new toolbox? Well, once you're not shackled to that additivity rule anymore, you can start defining all sorts of new measures. Think about it. If the value of A and B together doesn't have to equal A plus B, then that means it could be more than the sum, or it could be less, and that's exactly where these new tools come from.
First up, we have super additive measures. This is the math behind that idea of synergy. Going back to our TV, with a super additive measure, we can finally, formally say that the value of a great picture and great sound is greater than just adding their individual scores together.
And then you've got the flip side, sub-additivity. This is perfect for modeling things like redundancy or diminishing returns. For example, if you have two security systems that partially overlap, the total protection you get is less than the sum of what each one would give you individually. A sub-additive measure captures that perfectly.
And this is where things get really powerful. We can now deal with uncertainty in a much more intelligent way. Instead of being forced to come up with one single exact number for a probability, belief and plausibility measures let you use a range, an interval of possibilities. This is an absolute game changer when your information is spotty or different sources disagree, which happens all the time in fields like AI.
Okay, enough theory. We've got this awesome new toolbox. Let's see how it actually works in the real world, solving problems that the old rules just couldn't handle. Okay, check this out. This is a fantastic example. You've got a bunch of seismologists trying to pinpoint an earthquake's epicenter. See all those circles? Each one is an expert's opinion. They overlap, they conflict, it's a mess. Trying to use old-school probability here would be a total nightmare. But with belief measures, you can fuse all that messy, conflicting data into something genuinely useful, a probability range. So for that area A, we're not saying the probability is exactly 20%. We're saying it's somewhere between 13% and 33%. That's so much more honest and useful, right?
All right, let's bring it back to our trusty TV example. Look at this table. TV A has a perfect picture, 0 sound. TV B is the opposite, and TV C is just kind of okay, but it's balanced. Now, a simple additive model, like a weighted average, it completely fails. It actually gives the balanced TV the lowest score. But a non-additive model, using this cool tool called the Choquet integral, gets it right. You can think of it like a smarter kind of average, one that can actually reward that synergy. It sees the value in the balance of TVC and correctly says, yep, that's the best one.
And the big takeaway here is that this isn't just some abstract theory. This is the engine driving some really sophisticated stuff. From complex decision-making, to fusing information from different sensors, to building smarter AI systems that can actually reason with uncertainty. So if there's one thing to remember, it's this. By ditching that one simple rule of addition, we got a whole new mathematical language that's flexible enough to describe the world as it actually is. A world that's messy, full of interactions, and doesn't always just add up.
And that kind of leaves us with a really fascinating thought. If we can now start to put numbers on things that interact in these super complex ways, what else could we measure? Things we've always thought were impossible to quantify, like the trust within a team or the creative output of a group, maybe even happiness. Perhaps they're not immeasurable after all. Maybe we just needed a better toolbox.